Good morning, all, and a very warm welcome to respected Dr. Paresh Patel sir and Dr. Khushbu B. Desai, head of the department, to the third session of Symmetry and Groups Theory in Chemistry and its application. We are privileged to have Dr. Paresh Patel sir with us once again as he continues to share his expertise on their fundamental concepts. Sir, previous two lectures were incredibly valuable, offering deep insights into the complexities of symmetry and group theory. These sessions have provided us with a strong foundation, and we are confident that today's session will build upon that knowledge, enriching our understanding even further. We are truly grateful to have you, sir. Now, I would like to request Dr. Paresh Patel, sir, to continue with the session.
Thank you, Khushbu Madam and Abhishek sir. Good morning, one and all. So, dear students, yesterday we already discussed about the general introduction regarding the matrix and how to find out the inverse of the matrix, then multiplication, summation of matrix. Then we also discuss about the how to find out the class of water molecule and ammonia molecule. So today we are going for the matrix representation for the different symmetry operations. Means how to derive the matrix representations for the different symmetry operations, or we can say geometrical transformations of matrices. Geometrical transformations of matrices to how to find out the matrix representations. So first of all, we have to operate different symmetry operation on the molecule and find out the changes, and that changes can be represented in form of the matrix that is known as a matrix representations. So let us start first with the identity symmetry operation. So first one is identity. We already discussed that identity can be represented by capital E. Now, if we operate identity symmetry operation on any molecule, so molecule remains as it is. It means along the x-axis, so what will happen? E into x is equal to, there is no change, means 1 into x, 0 into y, and 0 into z. Similarly, E into y is equal to 0 into x. Along the y-axis, it should be 1, and along the z-axis, it is 0. E into z is equal to 0 into x plus 0 into y plus 1 into z. So this can be represented as E x y z is equal to 1 0 0 0 1 0 0 0 1 x y and z. So where E is equal to 1 0 0 0 1 0 0 0 1. So matrix representation for the identity symmetry operation can be represented by E is equal to 1 0 0 0 1 0 0 0 1 if the dimension of this matrix is three-dimensional. So dear students, how to find out the matrix representation for the identity? So just we have to mention that E is equal to 1 0 0 0 1 0 0 0 1. This is the matrix representation for the identity symmetry operation. Second symmetry operation is the rotational axis of symmetry, proper axis of rotation. Now, rotational axis can be represented in two ways. One is anti-clockwise as well as clockwise rotation. So, first of all, proper rotation, anti-clockwise. If we operate proper rotation anti-clockwise, then what will be the matrix? So, in this case, we have to operate a rotational symmetry operation on a two-dimensional system, and then we can extend it up to three-dimensional way, and on the basis of two-dimensional we can operate rotational axis first of all anti-clockwise. So what will happen in that? Suppose this one is the x-axis and y-axis. Suppose vector p with the coordinates x and y. Along the x-axis, the distance is x. vector P with the coordinates x and y, and length of this vector is r. So along the x-axis, the distance is x, and along the y-axis, the distance is y. Now, this angle is phi. Okay, so this is the initial position of this vector P with the coordinates x and y. It means along the x-axis, the distance is x, and along the y-axis, distance is y. Now, anti-clockwise rotation. It means if we rotate this vector P to P dash with the new coordinates x dash and y dash, and the angle is theta. So what will happen? The angle should be phi plus theta. The length of vector r remains as it is. Now in case of initial cos phi, this is right angle. This is right angle. So in this case, cos phi, this is phi. So the value for cos phi is equal to base divided by hypotenuse. So base means x and hypotenuse means r. So x is equal to r cos phi. Similarly, sin phi is equal to y by r, or we can say y is equal to r sin phi. So this is the initial position of this vector P. Now, if we rotate this vector P around theta, so overall angle will be phi plus theta. So we can represent it as cos phi plus theta is equal to the new length will be the x dash, and along the y-axis it will be y dash. So cos phi plus theta is equal to base. Base is nothing but the x dash by r. So x dash is equal to r cos phi plus theta. Similarly, sin phi plus theta is equal to y dash by r. So y dash is equal to r sin phi plus theta. Now simplify this. Distribute this both these equations. X dash is equal to r cos phi plus theta. We know that cos a plus b is equal to cos a cos b minus sin a sin b. In that way, it is nothing but the r cos theta cos phi minus r sin theta sin phi. We know that the value for cos phi is equal to x. So it is x cos theta minus value for r sin phi is equal to y sin theta. So this is the value for x dash. Similarly, y dash is equal to r sin phi plus theta. And we know that sin a plus b is equal to sin a cos b plus sin a cos b plus cos a sin b. So is equal to r sin 5 cos theta plus r cos 5 sin theta is equal to value for r sin phi is equal to y cos theta. Value for r cos theta is equal to x sin theta. Or we can write it as y dash is equal to x sin theta plus y cos theta. Okay. So if we simplify both this equation to give these two equations. X this is equal to x cos theta minus y sin, and y this is equal to x sin theta plus y cos theta. So we can write in form of the matrix. This is two-dimensional system. X this y this is equal to cos theta minus sin theta, sin theta, cos theta, x and y. This is P dash, this is P, and this is Cn, okay, anti-clockwise. So Cnk anti-clockwise can be represented as cos theta minus sin theta, sin theta, cos theta. Okay, so this is the rotation in the two-dimensional system. So we can extend it up to three-dimensional system. So Cnk anti-clockwise is equal to cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. Okay, so dear students, this is the matrix representations for anti-clockwise rotation. If we put the value of theta, then we can find out the matrix for the anti-clockwise rotation for any molecules. Okay, so this is the derivation. So remember that this is the derivation of anti-clockwise proper rotation. Next, matrix representations for clockwise rotation. Proper rotation for the clockwise. This is y-axis, this is x-axis. Now this is the vector p with the coordinates x and y, and angle along the x-axis is phi. This is right angle. The distance, the length of the vector p is r. So this is right angle. So we can write cos phi is equal to the vector p with the coordinates x and y. It means along the x-axis the distance is x, and along the y-axis the distance is y. So cos phi is equal to base divided by hypotenuse. Base is nothing but the x, and hypotenuse the length of the vector r. So x is equal to r cos phi. Similarly, sin phi is equal to front side divided by hypotenuse. Front side is nothing but the y divided by r. So y is equal to r sin phi. Now, matrix representations for clockwise proper rotation. It means if you rotate vector p to p dash, the new coordinates are x dash and y dash. It means along the x-axis the distance is x dash, and along the y-axis the distance is y dash, and this is theta. It means the overall angle is, this is phi minus theta. This is phi minus theta. So we can represent cos phi is equal to cos phi minus theta is equal to. Now the resultant angle is phi minus theta. So cos phi minus theta is equal to base x dash divided by hypotenuse r. So x dash is equal to r cos phi minus theta. Similarly, sin phi minus theta is equal to y dash by r. So y dash is equal to r sin phi minus theta. Now simplify both this equation. So x dash is equal to r cos phi minus theta. We know that cos a minus b is equal to cos a cos b plus sin a sin b. So is equal to r cos 5 cos theta plus r sin 5 sin theta. We know that the value for r cos phi is equal to x cos theta. R sin 5 is equal to y sin phi sin theta. This is the value for x dash. Similarly, y dash is equal to r sin phi minus theta. We know that sin a minus b is equal to sin a cos b minus cos a sin b. So r sin 5 cos theta minus r cos 5 sin theta is equal to r sin 5 is equal to y cos theta minus value for x r cos phi is equal to x sin theta. So minus x sin theta plus y cos theta. So we have two equations. One which is related with the x dash and y dash. So x dash is equal to x cos theta plus y sin theta, and y dash is equal to minus x sin theta plus y cos theta. Okay, now we can represent this two-dimensional system in form of the matrix x dash y dash is equal to cos theta sin theta minus sin theta cos theta, x and y. This is the vector for p dash, this is for p, and this is k clockwise rotation. Okay, so we can write c and k clockwise is equal to cos theta sin theta minus sin theta cos theta. So this is the two-dimensional system. We can extend it up to three-dimensional system. So C and K clockwise is equal to cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. So dear students, this is the matrix representations for clockwise rotation, and with the help of this equation we can find out the symmetry operation for the proper rotation as a clockwise rotation. As for example, I can give an example. Water molecule consists C2 axis of symmetry. So in that case, we have to rotate the water molecule around 180. So water molecule consists E C2 sigma Vxz sigma V YZ symmetry operation. So in case of matrix representation for C2, in this case, we have to put the value theta is equal to 180, cos 180, sine 180, 0. Minus sine 180, cos 180, 0. 0, 0, 1. So we know that the value for cos 180 is equal to minus 1. Sine 180 is 0, 0. Sine 180 is 0. Cos 180 minus 1, 0, 0, 1. So this is the matrix representation for C2 or C21. Both are the same. Okay. So dear students, with the help of this equation, we can find out the matrix representation for proper rotation for the clockwise. Now, in case of anti-clockwise rotation, we can put the value theta is equal to 1, theta is equal to angle of rotation in that equation. So we can find out the value of proper rotation for the anti-clockwise rotation. Now, next symmetry operation is a reflection. In case of the reflection, third one is reflection operation. Now, in the case of the reflection, we have to consider vector P with the x and y coordinates and reflects through yz plane. Suppose vector P, this is x-axis, this is y-axis. Suppose vector P with the coordinates x and y. The length of this vector is r. Now, a reflection through yz plane. It means this is the yz plane. So what will happen to give the reflected vector is p dash with the coordinates x dash and y dash. It means along the x-axis the distance is x dash and along the y-axis it remains same. So now if we reflect the vector p through the yz plane, so the new coordinates along the x-axis, the x becomes minus x. So that can be represented as minus 1 and 0 remains as it is. There is no change in the along the y-axis. The distance remains same. It means 0. Along the y-axis, what will happen? X is 0 and y remains as it is as a plus 1. So this can be represented in form of the matrix. So x dash, y dash is equal to minus 1, 0, 0, 1. X and y. So this is p dash, this is p, and this is sigma yz. This can be represented as sigma yz. Minus 1, 0, 0, 1. Now this is two-dimensional system. We can extend it up to three-dimensional system is equal to minus 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is the matrix representations for sigma yz. We can write the matrix representations for sigma xz. Here sigma yz, it means this is along x-axis, this is along y-axis, this is along z-axis. Means yz means x is minus 1. So similarly, sigma xz can be represented as 1, 0, 0, 0 minus 1, 0, 0, 0, 1. Similarly, sigma matrix representations for sigma xy. So in that case, 1, 0, 0, 0 minus 1, 0, 0, 0, 1. So dear students, remember that this value is along the x-axis, this value is along the y-axis, and this value is along the z-axis. So sigma xy can be represented as 1, 0, 0, 0, 1, 0, 0, 0, minus 1. So this is the matrix representations for reflection operation as a sigma yz, sigma xz, and sigma yz. Now, fourth symmetry operation is improper axis. Fourth symmetry operation is improper axis of symmetry, or we can say rotational reflection axis of symmetry, that can be represented as Nk is equal to Cnk sigma h. Now, in case of the sigma h, this is clockwise. So Snk is equal to matrix representation for the clockwise rotation, cos theta, sin theta, we already proved this, minus sin theta, cos theta, 0, 0, 0, 1. This is the matrix representations for clockwise rotation. Now, dear students, what is the value for sigma h? Always remember that sigma h is always perpendicular to z axis, means the sigma h is nothing but the sigma xy plane. This is nothing but the sigma xy plane. This is perpendicular to the z axis. Means value is 1, 0, 0, 0, 1, 0, 0, 0, minus 1. This is three-dimensional matrix. If you go for the combinations of this three-dimensional matrix and this three-dimensional matrix, result will be cos theta, sin theta, 0, minus sin theta, cos theta, 0, 0, 0, minus 1. This is the matrix representations for improper axis of symmetry, or we can say this is a rotational reflection axis of symmetry. Now, last symmetry operation is fifth one is inversion, or we can say center of symmetry inversion operation. And this can be represented as I, small I. So inversion of operation can be represented by small I. Now, what will happen in the case of inversion along the x-axis? So x becomes minus x, y becomes 0, z becomes 0. Along the y-axis, what will happen? X becomes 0, y becomes minus 1, and z becomes 0. X becomes 0, y becomes 0, and z becomes 0. So x, y, z is equal to minus 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1, x, y, and z. So I is equal to minus 1, 0, 0, 0, 1, 0, 0, 0, 0, minus 1. So this is the matrix representations for inversion of symmetry, or we can say center of symmetry. So dear students, these are all are the derivation of different symmetry operations. Now, how to find out the symmetry matrix representations? How to give the matrix representations for different molecules? As for example, give the matrix representations for water molecule. Okay, we know that water molecule consists E, C2, sigma Vxz, sigma Vyz symmetry elements. Okay, now if we go for the symmetry operation, we already discussed that matrix representations for identity is nothing but the 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is the matrix representations for identity symmetry operation. If we operate C2 or C21, then we have to put the value as a proper rotation cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. So value for cos theta is equal to cos 180 sin 180 0 minus sin 180 cos 180 0 0 0 1 is equal to minus 100 0 minus 10 0 0 1. The value for cos 180 is equal to minus 1. Okay, in case of water molecule, we know that either we have to go for the clockwise rotation or anti-clockwise. Answer will be the same. So if we put the value in a anti-clockwise rotation, then what will happen? The equation for the anti-clockwise rotation is cos theta minus sin theta 0 sin theta cos theta 0 0 0 1. Okay, in this equation, so cos 180 is equal to minus 1, sin 180 is 0 0, sin 180 is 0, cos 180 minus 1 0 0 0 1. So this is the matrix representations for anti-clockwise rotation. So dear students, in case of the water molecule, if we rotate the molecule along the main principal axis either clockwise or anti-clockwise, the matrix will be the same. So C21 minus 1 0 0 0 minus 1 0 0 0 1. Now what about sigma v xz and sigma v yz? We already discussed about the sigma v xz. Sigma v xz is nothing but the 1 0 0 0 minus 1 0 0 0 1. We already derived. Sigma v yz is equal to minus 1 0 0 0 1 0 0 0 1. Okay, so dear students, these are the matrix representations for water molecule. Okay, just these are the representations. So how to derive the matrix representations for water molecule? This is the matrix. Next molecule is ammonia molecule. The shape of the ammonia molecule is pyramidal. It consists E, C3 plus, C3 minus, sigma Va, sigma Vb, and sigma Vc. Okay, so now matrix representations for identity symmetry operation. E is equal to 1 0 0 0 1 0 0 0 1. C3 plus. Another symmetry operation is C3 plus or C3 1. Means we have to rotate ammonia molecule along the main principal axis around 120 as a clockwise rotation. Then if you put the value cos 120 sin 120 0 minus sin 120 cos 120 0 0 0 1. So is equal to value for cos 180 is equal to minus 1 half sin 1 half sin 120 root 3 by 2 0 minus root 3 by 2 minus 1 half 0 0 0 1. So this is the matrix representation for C3 plus, or we can say C3 1. This can be represented as a C3 1. Now matrix representation for C3 minus. In case of C3 minus, we have to rotate the ammonia molecule along the main principal axis around 120 as an anti-clockwise rotation. So cos theta. Now equation for the anti-clockwise rotation, cos theta minus sin 20 means cos 120 minus sin 120 0 sin 120 cos 120 0 0 0 1. So value for cos 180 minus 1 half root 3 by 2 0 root 3 by 2 minus 1 half 0 0 0 1. So this is the matrix representations for C3 plus, or we can say rotation of the anti-clockwise rotation. Now sigma Va. Okay, so dear students, remember that in ammonia molecule, all the three vertical planes are the examples of sigma yz plane. So dear students, remember that all the vertical planes in the ammonia molecules are a yz plane. So sigma Va is equal to minus 1 0 0 0 1 0 0 0 1. Similarly, sigma Vb, all are the yz plane, means the value will be the same, 0 1 0 0 0 1. Sigma Vc, minus 1 0 0 0 1 0 0 0 1. Okay, so dear students, these are the matrix representations for E, C3 plus, C3 minus, sigma Va, sigma Vb, and sigma Vc. Now, last example is a trans-dichloroethylene. Trans-dichloroethylene consists E, C2, sigma H, and I symmetry elements. If we operate identity symmetry operation, there is no change. It means matrix should be 1 0 0 0 1 0 0 0 1. C2, if you put the value cost, theta is equal to 180 to give the matrix will be the same, 0 minus 1 0 0 0 1. Sigma H, we know that sigma H is nothing but the sigma xy plane, 1 0 0 0 1 0 0 0 minus 1. XY plane means the value for z is negative. I is equal to minus 1 0 0 0 minus 1 0 0 0 minus 1. This is the matrix representations for inverse of the symmetry, or we can say these all four are the matrix representations for trans-dichloroethylene. Now, next title, dear students, next title, and this title is very important. But before that, uh, I think laws of the four laws of the group. So first law is law of identity. So what is law of identity? If the combination of identity symmetry operation with any symmetry operation, answer will be the same. As for example, water molecule consists E, C2, sigma Vxz, sigma Vyz symmetry elements. So E into C2 is equal to C2 into E. Answer will be the C2. So matrix left hand side is equal to E into C2. So matrix representation for identity 1 0 0 0 1 0 0 0 1. And matrix representation for C2 we already derived, 0 minus 1 0 0 0 1. If you combine these three-dimensional matrices to give minus 1 0 0 0 minus 1 0 0 0 1. This is the left hand side. The right hand side is equal to C2 into E, minus 1 0 0 0 minus 1 0 0 0 1. And identity 1 0 0 0 1 0 0 0 1. If we combine these matrices to give minus 1 0 0 0 minus 1 0 0 0 1. Okay, so this is the first law of the group, law of identity. Combination of any symmetry operation with identity, our answer will be the same. Second law of the group is the law of combination or multiplication. What is law of combination or multiplication? Combination of any two symmetry operations. Answer will be the third element of the same group. As for example, water molecule consists E C2 sigma Vxz sigma Vyz. So C2 into sigma Vyz is equal to sigma Vxz. So left hand side is equal to C2 into sigma Vyz. Matrix representation for C2 minus 1 0 0 0 minus 1 0 0 0 1. This is the matrix representation for C2. Sigma Yz minus 1 0 0. Sorry. Yes. 0 0 1. So overall result 1 0 0 0 minus 1 0 0 0 1. And right hand side is equal to 1 0 0 0 minus 1 0 0 0 1. Okay, so this is the law of combination. Now, law of association. A cross B into C is equal to A cross B cross C. So, in case of the water molecule, C2 into sigma Vxz into sigma Vyz is equal to C2 into sigma Vxz sigma Vyz. The left hand side is equal to matrix representations for C2 minus 1 0 0 0 minus 1 0 0 0 1. Sigma Vxz 1 0 0 0 minus 1 0 0 0 1. And sigma Vyz 1 minus 1 0 0 0 minus sorry 0 1 0 0 0 1. This is the matrix representation for sigma Yz. So first of all, we have to go for combination of these two matrices to give minus 1 0 0 0 1 0 0 0 1, and then combination with minus 1 0 0 0 1 0 0 0 1 is equal to 1 0 0 0 1 0 0 0 1. So left hand side is equal to 1 0 0 0 1 0 0 0 1. Now in case of right hand side, first of all we have to combine these two and then combine with this. So is equal to minus 1 0 0 0 minus 1 0 0 0 1. Combination of these two matrices to give minus 1 0 0 0 minus 1 0 0 0 1. Now combination of these two matrices to give 1 0 0 0 1 0 0 0 1. So this is the left hand side is equal to right hand side, or we can say this is the law of association. Now last law of group is law of inverse. Combination of any symmetry operation and its inverse, answer will be the identity. This is known as law of inverse. As for example, in case of water molecule, C21 into C21 inverse, answer will be the identity. Left hand side is equal to matrix representation for C21 minus 1 0 0 0 minus 1 0 0 0 1, and C21 inverse, both are the same, minus 1 0 0 0 1 0 0 1. So combination of these two matrices to give 1 0 0 0 1 0 0 0 1 is equal to right hand side. So these are the four laws of the group. So dear students, we are going for the most important title for your exams, and the name of our title is so dear students, reducible and irreducible representations. So what are reducible and irreducible representation? As for example, A, B, C, D, E, P. These are the different matrices. And if you go for the P dash, A into P is equal to A dash. P dash B into P is equal to B dash. P dash P inverse C P is equal to C dash, etc. And if you go for the resultant matrix, A1 0 0 0 0, 0 A2 0 0 0, 0 0 A3 0 0, 0 0 0 A4 0, 0 0 0 0 A5. Okay, this is the 5-dimensional matrix, and we can we can convert this 5-dimensional matrix into lower dimensional matrix or 1-dimensional matrix. So this representation can be represented as a reducible representations. So dear students, uh, always we have to consider uh, identity symmetry matrix to consider the dimension of any representation. Okay, so in case of, we can convert higher dimension matrix, or we can reduce higher dimension matrix into lower dimension matrix, so that representation can be represented as a reducible representation. As for example, water molecule consists E C2 sigma Vx sigma V YZ symmetry elements. Matrix representation for identity symmetry operation 1 0 0 0 1 0 0 0 1. Matrix representation for C2 minus 1 0 0 0 minus 1 0 0 0 1. Sigma Vxz 1 0 0 0 minus 1 0 0 0 1. Sigma Vyz minus 1 0 0 0 1 0 0 0 1. Okay. So these are the different matrices for the water molecules, symmetry operations of the water molecule. Now, the dimension of this matrix, we already discussed that the dimension of any representation can be decided from the matrix representation for identity symmetry operation. Okay, this is 3-dimensional matrix, 3 by 3 matrix. It means the dimension of this representations is 3-dimensional. Now, 1, 2, 3, and 4. These are the 4 matrices of the water molecule identity C2, sigma Vx and sigma Vyz. Now, this is 3-dimensional matrix, or we can say this is the 3-dimensional representations. Now, we can convert these 3-dimensional representations into lower dimension matrix, so that representations can be represented as a reducible representation. Now, the dimension of this matrix is 3. Okay, now we can convert this 3-dimensional matrix C2V E C2 sigma Vxz sigma Vyz. Okay, this is along x-axis, this is along y-axis, this is along z-axis. Okay, suppose x, y, and z. Now we can write identity symmetry operation 1 and 1. So 1, 1, 1, 1, 1, 1. C2 minus 1, minus 1, and 1. Sigma Vxz 1, minus 1, and 1. This is along x-axis, this is along y-axis, this is along z-axis. Similarly, yz minus 1, 1, and 1. Clear? So, dear students, we can reduce this three-dimensional matrix into one-dimensional matrix. So, these representations are reducible representations. Okay, so we can reduce this three-dimensional matrix into one-dimensional matrix. So, this representation can be represented as a reducible representation. Now, what is irreducible representation? If we can't reduce higher dimension matrix into lower dimension matrix, that representation can be represented as a irreducible representation. So less than one dimensional is not possible. So all one dimensionals are the examples of the irreducible representations. So dear students, we can't reduce the lower dimension, higher dimension matrix into lower dimension matrix. So that representations can be represented as a irreducible representation. So these are the reducible representations, and these are the irreducible representations. So dear students, this is most important questions for your annual exams, that what are reducible and irreducible representations, give reducible and irreducible components of the water molecules. So these are the reducible and these are the irreducible components for the water molecule. Now, second examples for the reducible and irreducible representations. Second example is the ammonia molecule. Ammonia molecule consists E, C3 plus, C3 minus, sigma Va, sigma Vb, and sigma Vc symmetry elements. So matrix representations for identity 100, 010, 001. C3 plus. We already derived this matrix representations for ammonia molecule. Minus 1/2 root 3 by 2, 0. Minus root 3 by 2. Minus 1/2 root 3 by 2, sorry. Root 3 by 2 minus 1/2, 0, 0, 0, 1. Matrix representation for C3 minus. This is for anti-clockwise rotation. Minus 1/2. Clockwise rotation, cos theta, sin theta, 0. Minus sin theta, cos theta, 0. It means this is minus root 3 by 2 and this is plus root 3 by 2. Sigma VA, 10, minus 100, 010, 001. Sigma VB, minus 100, 0 minus 10, 001. This is plus 1. Sigma VC, minus 100, 010, 001. So what is reducible representation? We can reduce higher dimension matrix into lower dimension matrix. So that representation can be represented as a reducible representation. Now, the matrix representation for identity symmetry operation is a three-dimensional representations. So this is known as a reducible representation. We can reduce this three-dimensional matrix into lower dimensional matrix. But we have to remember that in case of ammonia molecule, we have to perform the symmetry operation on the x and y axis, as of both this symmetry operation on the say x and y as a symmetry operations on both this x and y axis, and we can't separate that along the axis and y axis. So that's why we can convert this three-dimensional matrix into two-dimensional and one-dimensional representations, just like this one. So we can convert this three-dimensional matrix into C3V, E twice C3, 3C2. 10 along the x and y, z. 0 into 1 and 1. Okay, you can take either this C3 plus or this C3 minus. Both are the same. Why? The character of this matrix is minus one half, already minus one. Here minus one half, totally minus one. It means you can take this matrix or this matrix, both are the same. C2, all are the same. You can take anyone. So dear students, these are the reducible and irreducible components of the ammonia molecule. So this is most and most important questions for you. Give the what are reducible and irreducible representations. Give reducible and irreducible components of the water molecule or ammonia molecule. So you have to mention this. Next data list. Relationship between reducible and irreducible representations. Relationship between the reducible and irreducible representations can be represented as 1 upon h. Ni is equal to 1 upon h. Summation of character r into r. Character r into r into n means number of the symmetry elements I into r. So this is the number of times that symmetry operation. H represents order of a group. This is the character for reducible representations. N is equal to number of that symmetry operation. Character I into R. It means this is a character for irreducible representations. Now, take one example. Suppose C3V E twice C3 3 sigma V. The reducible representations is 5 2 minus 1. Now, this is reducible representation. Why reducible representation? The character of identity symmetry operation is 5. So we have to reduce this reducible representation with the help of these equations between reducible and irreducible representations. For this conversion, we need a character table for C3V point group. A1, A2, E. 1, 1, 1, 1, 1, minus 1, 2, minus 1, 0. This is the character table for C3V point group. Okay, exam point of view, you have to provide this. You will provide this character table. Okay, just like our log table. So with the help of this character table and with the help of the relation between reducible and irreducible representation, we can convert these reducible representations into irreducible representations. So let us start first of all N1. N1 which corresponds to A1 irreducible representations. So first of all, order of a group is equal to 6. Why? 1 plus 2 plus 3. Order of a group represents numbers of the symmetry elements are present in a molecule. So ammonia molecule consists 6 symmetry elements. So we can represent as a 1 by 6. Now summation of character R and character irreducible representation. Now character for irreducible representation is 5. Then N, numbers of symmetry element operation is 1. Then irreducible representation 1 plus 5 1 1. Sorry, this is for A1. It means 2 2 1. 2 reducible, 2 number of n is equal to 2 and irreducible component is 1 plus minus 1 is the reducible 3 is the numbers of the symmetry operation, and 1 is the irreducible component, is equal to 1 by 6, 5 plus 4 minus 3 is equal to 1. So the value 4 and 1 is equal to 1 and 2. So how to find out the n1? So these are the reducible representation. These are the numbers of symmetry operation, and these are the irreducible component. So n1 with respect to a1. So first, this is reducible representation 5, 1, 1, 2, 2, 1, minus 1, 3, 1. Okay, is equal to 1 and 2. 1 by 6, 5, okay, and 2, which corresponds to a2. 5, 1, 1 is equal to 5. 2, 2, 1, it means 4. 3 minus 1 is equal to plus 3 is equal to 2. The value 4 and 2 is equal to 2. Value 4 and 3, 1 by 6. Now n3, which corresponds to E. 5, 1, 2, 10. 2, 2 minus 1 minus 4 plus 0 is equal to 1. It means value 4 and 1 is equal to 1, and 2 is equal to 2, and 3 is equal to 1. C3V E twice C3, 3 sigma V. A1, N1 is equal to 1, N2 is equal to 2, N3 is equal to 1. So N1 is equal to 1 means N1 one time. 1, 1, 1. N2 two times means A2 two times. 1, 1, minus 1, 1, 1, minus 1. E only one time. 2 minus 1 is 0. Okay. 2 plus 1 plus 1 plus 1, 5. Minus 1, 1, 1, 1, 2. 0 minus 1 minus 1, 1. It means minus 1. So this is a reducible representation. We can convert this reducible representation with the help of this relation between reducible and irreducible representations and character table for C3V point group. So these are the irreducible components. Okay, so dear students, we can convert these reducible representations into irreducible component. Dear students, now we are going for the another most important title is the great orthogonal theorem. The great orthogonality theorem dear students, exam point of view, this is also most important. Now, what is great orthogonal theorem? Great orthogonal theorem is concerned with the element and which constitute the irreducible representations of a group. The mathematical statement of the great orthogonal theorem is summation of R, tau I R M N T J R M dash N dash is equal to H by, just a minute, summation of T I R M N T J R M dash N dash is equal to H by square root Li Lj delta Ij, delta mm dash and delta nn dash. So great orthogonal theorem is concerned with the element of the matrices which constitute the irreducible representations. The mathematical statement of the great orthogonal is as follows. H represents order of a group. Li and Lj represents dimension of matrices. Dimension. Li and Lj, these are the dimensions of the matrices. This is the element of the mth row and column of the ith irreducible representations. This is the element of the mth row and this column of the jth irreducible representation, or we can say this is the complex conjugations. Now, with the help of normalized condition as well as orthogonality theorem, we can consider both this theorem to the our great orthogonal theorem, or we can derive the three sub mathematical statement from the great orthogonal theorem. So summation of r ti r mn tj r mdes ndest is equal to 0, where I is not equal to g. It means elements of the matrices of the different irreducible representations are orthogonal to each other. This is the first sub mathematical statement of the great orthogonal theorem. Second one, summation of TIR MN TIR MDEST NDEST is equal to 0. Here M is not equal to MDEST, N is not equal to NDEST. It means the elements of a different sets of the matrices of the same irreducible representations are orthogonal to each other. So repeat again. This is the mathematical statement of the great orthogonal theorem. This is the first sub-mathematical statement of the great orthogonal theorem. Element of the corresponding matrices of the different irreducible representations are orthogonal. Here, the irreducible representations are the same. It means elements of the different sets of the matrices of the same irreducible representations are orthogonal to each other. And third one is nothing but the summation of R TIR MN TJ R MDEST NDEST is equal to H by Li. Okay, this is possible only if the values of delta ij is equal to delta mmdest is equal to delta nndest is equal to 1, and value of li is equal to lg. If li is equal to lg, it should be li square. Square root li square means square root li square is equal to li, and the value of delta ij, delta mmdest, delta nndest is equal to 1. So to give, this is the third sub mathematical statement of the great orthogonal theorem. Okay, so dear students, these are the mathematical statement of the great orthogonal theorem. Now, consequences of great orthogonal theorem, or we can say 5 properties of irreducible representations from the great orthogonal theorem, or it can also be recognized as the consequences of the great orthogonal theorem. So first one, the numbers of irreducible representation is equal to numbers of the classes. As for example, in case of water molecule, E C2 sigma Vxz sigma Vyz, A1, A2, B1, B2. 1, 1, 1, 1, 1, 1, minus 1, minus 1, 1, minus 1, minus 1, 1. Dear students, this is the character table for C2V point group. In case of the C2V point group, this is the character table for C2V point group. So first characteristics of the irreducible representations. The numbers of irreducible representation is equal to numbers of the classes. In case of the water molecule, we already discussed in the previous lectures. Water molecule consists four symmetry elements and numbers of the classes also four. First one is identity, second one is C2, third one is sigma VXZ, and fourth one is sigma VYZ. It means numbers of the classes is equal to 1, 2, 3, and 4. So numbers of irreducible representations is equal to numbers of the classes. So numbers of the classes is equal to 4. It means numbers of irreducible representations should be equal to 4. 1, 2, 3, 4. Second one, the sum of the square of the dimension. The sum of the square of the dimension. Second properties or second characteristics. The sum of the square of the character. Sum of the square of the dimension is equal to order of a group. So we always consider dimension with respect to identity symmetry operation. This is one dimensional, one dimensional, one dimensional, one dimensional. So 1 square plus 1 square plus 1 square plus 1 square is equal to 4. So order of a group for water molecule is equal to 4. So second characteristics of irreducible representations, the sum of the square of the dimension is equal to order of a group. Third characteristics, the sum of the square of the character is equal to order of a group. 1, 1, 1, 1. These are the character. 1, 1, minus 1, minus 1. These are the character. Okay. The sum of the square of the character is equal to order of a group. It means character 1 is square. Character 1 C2 square. Character 1 sigma V XZ square plus character 1 sigma V YZ square is equal to order of a group. So in this case, 1 into 1 square, 1 into 1 square, plus 1 into 1 square, plus 1 into 1 square. So is equal to 4. Clear? So third characteristics of the irreducible representations, the sum of the square of the character is equal to order of a group. Now fourth one. Fourth characteristics of irreducible representations. Any two irreducible representations are orthogonal to each other. It means 1 into 1 into 1, 1. 1 into 1 into 1. 1 into 1 into minus 1, minus 1. 1 into 1 into minus 1. Minus 1 is equal to 0. So any two irreducible representations are orthogonal to each other. This is the fourth characteristics. And last one is the character of the element of the same class of an reducible and irreducible representations are the same. Okay, so dear students, these are the 5 characteristics of irreducible representations, or we can say these are the 5 consequences of great orthogonal theorem. And with the help of these 5 characteristics of irreducible representations, we can derive the character table for C2B point group as well as C3B point group. 2 character tables are in our syllabus. So what is character table? The definition for the character table, the devices can be utilized for the applications of group theory and molecular symmetry is known as character table. So what is character table? The devices can be utilized for the molecular symmetry and group theory is known as character table. So dear students, to construct a character table of water molecule and ammonia molecules, these 2 character tables are in our syllabus. So exam point of view, this is also most important to derive or to construct a character table for water molecule or ammonia molecule. So let us start with the first, construct a character table for construct a character table for C2B point group, or construct a character table for water molecule, sulfur dioxide molecule, H2S molecules, all are the same. So dear students, remember that construct a character table for C2B point group, or construct a character table for water molecule, construct a character table for H2S molecule, or construct a character table for sulfur dioxide molecule, all are the same. So let us start with the, okay. it is most important, and we have to attempt this question first in the exam. Why? The We know the answer of these questions, so we have to derive this character table: C2V E C2 sigma V X Z sigma V Y Z A1 A2 B1 B2 1 1 1 1 1 1 minus 1 minus 1 1 minus 1 1 minus 1 1 minus 1 minus 1. We have to derive this character table. So let us start first. Let us consider water molecule. In case of C2V point group, let us consider water molecule. It consists C2V point group, and it consists it belongs to C2V point group. It consists E C2 sigma VXZ and sigma VYZ symmetric elements. So dear students, first of all, how to construct the character table for C2V point group? Let us consider water molecule. It belongs to C2V point group. It consists E C2 sigma VXZ and sigma VYZ symmetry elements. Okay. So what will be the first characteristics of irreducible representations? The numbers of irreducible representation is equal to numbers of the classes. So first of all, we have to find out the classes of water molecule or C2V point group. E is conjugated to itself to form an individual class. C2 conjugated to itself to individual class. Sigma VXZ conjugate to itself to form an individual class. Sigma VYZ conjugate to itself to form an individual class. Individual class, yes. So numbers of the classes is equal to 4 in case of water molecule. So we can write it as C2V E C2 sigma VXZ sigma VYZ. So these are the 4 classes. It means according to the rule number first, characteristics number first, the numbers of classes is equal to numbers of the irreducible representation. So here numbers of the classes is equal to 4. It means number of irreducible representation should be equal to 4. Next, rule number second or characteristics number second, the sum of the square of the character is equal to order of a group. Suppose this one is character 1E. This is known as character 1C2. This is character 1 sigma VXZ. Character 1 sigma VYZ. So what is rule number second? The sum of the square of the character is equal to order of a group. So character 1 is square plus character 1 C2 square plus character 1 sigma VXZ square plus character 1 sigma VYZ square is equal to order of a group. In case of water molecule, order of a group is equal to 4. Now, character may be positive or may be negative, but to maintain the uniformity of any character table, first irreducible representation should be with respect to plus 1. Suppose if we take 1, so 1 square, 1 square, 1 square, 1 square is equal to 4. Means this can be satisfied. So first irreducible representation 1, 1, 1 and 1. Chalo, next one. Suppose this one is character 2E, character 2C2, character 2 sigma VXZ, character 2 sigma VYZ. Now rule number 3. Just a minute. Rule number, I think, second. The sum of the square of the dimension. The sum of the square of the dimension is equal to order of a group. Suppose this one is L1, L2, L3, L4. The sum of the square of the dimension is equal to order of a group. L1 square, L2 square, L3 square, L4 square is equal to order of a group. Okay, here order of a group is equal to 4. And negative dimension is not possible. So minimum dimension is 1, then it can be satisfied. So 1, 1, 1, and 1. First of all, we have to go for the first characteristics of the irreducible representation. Numbers of the classes is equal to numbers of irreducible representation. Then we have to go for the second characteristics. The sum of the square of the dimension is equal to order of a group. Then we have to go for the characteristics number 3. The sum of the square of the character is equal to order of a group. Now for character 2 C2, character 2 sigma v xj, character 2 sigma v yz. Okay. According to the characteristics number 4, any two irreducible representations are orthogonal to each other. So T1 and T2, 1 into 1 into 1 is equal to 1 plus 1 into 1 into character T2 plus 1 into 1 into character sigma v xz plus 1 into 1 into character sigma v yz is equal to 0. This equation can be satisfied if the character for any two values are the -1 and any one value is +1, then this can be satisfied. Suppose this one is 1 and these are the -1. This equation can be satisfied. But these characters should be satisfied the characteristics number 3. What is the 3? Characteristics number 3. Suppose this one is 1, -1, and 1. What is the characteristics number 3? The sum of the square of the character is equal to order of a group. 1 into 1 square, 1 into 1 square, 1 into -1 square, 1 into -1 square is equal to 4. So this can be satisfied. So we can write the second irreducible representation is 1, 1, -1, and -1. Now to get the third irreducible representation, character 3 sigma, C2, character 3 sigma v xz, character 3 sigma v yz. Again, characteristics number 4. First of all, we have to go for the T1, T3 or T2, T3. So what will happen? So first T1 and T3. So 1 into 1 into 1, 1. Any two irreducible representations are orthogonal to each other. 1 into 1 into character 3C2. 1 into 1 into character 3 sigma v xz. 1 into 1 into character 3 sigma v yz is equal to 0. This is the equation number 1. Similarly, T2 and T3, it means 1 plus character 3C2 minus character 3 sigma v xz minus character 3 sigma v yz is equal to 0. This is the characteristics number. Now, this is the equation number 2. Now, add equation 1 into 2. So, what will happen? These are cancel out. 2 plus 2 character 3C2 is equal to 0. It means character 3C2 is equal to -1. So the value for character 2 is equal to -1. Now substitute value in any one equation. 1 -1 plus character 3 sigma v xz plus character 3 sigma v yz is equal to 0. Okay, it means character 3 sigma v xz is equal to minus character 3 sigma v yz, or we can say 1 is equal to -1. Means the value for the character 3 sigma v xz is equal to +1. Then character 3 sigma v yz should be -1, or this one is -1, then it should be +1. Suppose the value for character 1, this one is -1, but this can be satisfied. The characteristics number 3, the sum of the square of the character is equal to order of the group. Now to get the character for the fourth irreducible representations, now according to the characteristics number 4, any two irreducible representations are orthogonal to each other. Suppose T1 and T4. So 1 into 1 into 1 into 1 is equal to 1. 1 into 1 into character C4. 1 into 1 into character 4 sigma v xz plus character 4 sigma v yz is equal to 0. Similarly, T to T4. So 1 plus character 4 C2 minus character 4 sigma v xz minus character 4 sigma v yz is equal to 0. This is equation number 1 and this is equation number 2. Add equation 1 into 2. Both are cancelled out. 2 plus 2 character 4 C2 is equal to 0. So character 4 C2 is equal to minus 2. Sorry, minus 1. So the value for minus 1. Now substitute this value in above one equation. 1 minus 1 character 4 sigma v xz plus character 4 sigma v yz is equal to 0. It means character 4 sigma v xz is equal to minus character 4 sigma v yz. It means 1 is equal to minus 1. So again, if the value for sigma v xz is equal to plus 1, then character 4 sigma v yz should be minus 1. Okay. In previous one, we have taken character 3 sigma v xz is equal to plus 1. So if we take minus 1, then it should be plus 1. But it should be satisfied the characteristics number 3. The sum of the square of the character is equal to order of a group. So again, 1 into 1 square, 1 into minus 1 square, 1 into minus 1 square, 1 into 1 square is equal to 4. So these are the different characters for the 4 irreducible representations. Now we are going for the Mulliken symbols. Okay. For the any irreducible, one-dimensional irreducible representations, A and B can be used. For the two-dimensional representations, E can be used. And for three-dimensional, T and F can be used. Okay, to represent any one-dimensional irreducible representations, A or B can be used. For two-dimensional, E can be used. And for the three-dimensional, T and F can be used. Okay, 1, 1, 1, 1. So all are the one-dimensional. So A or B can be used. So when A can be used and when B can be used, if the character 4 main principal axis is plus 1, so later capital letter A can be used. If the character 4 main principal axis is minus 1, then capital letter B can be used. So here character plus 1 A can be used. Character plus 1, this is minus 1, B can be used, minus 1, so B can be used. Next one. Now, subscript 1 and 2. If C2 is perpendicular to the main principal axis and character of that perpendicular C2 axis is plus 1, subscript 1 can be used. And character of that perpendicular C2 axis is minus 1, then subscript 2 can be used. But in case of water molecule, only one principal axis C2 is present. There is no perpendicular C2 axis are present in the water molecule. So we have to go for the next one. So next one is character sigma xz. So if the value for character sigma xz is plus 1, then subscript 1 can be used. And if the value for character sigma v xz minus 1, then subscript 2 can be used. Here 1, it means 1. Here minus 1 means subscript 2 can be used. Here 1 and here minus 1 means 2 can be used. So this is the construct the character table for C2V point group. So dear students, this is the most important questions for you. So next one. Construct a character table for C3V point group. Or we can say construct the character table for ammonia molecule, or construct a character table for PO shell 3 molecule, or construct a character table for chloroform molecule. Dear students, construct the character table for C3 point group or construct the character table for PO3 molecules or construct the character table for ammonia molecules, chloroform molecule, all are the same. Now let us start construct the character table for C3V point group. C3V E twice C3 3 sigma V A1 A2 E 1 1 1 1 1 minus 1 2 minus 1 0. This is the answer of this questions. So dear students, first of all let us consider ammonia molecule. It belongs to C3V point group. It belongs to C3V point group. It consists E C3 plus C3 minus sigma Va, sigma Vb, and sigma Vc symmetry elements. First of all, E conjugate to itself to form an individual class. C3 plus C3 minus conjugate to each other to form a combined class. Sigma Va, sigma Vb, sigma Vc conjugate to one another to form a combined class. Okay. So in case of the ammonia molecule, numbers of the classes is equal to 3. 1 identity, 2 C3, and 3 sigma V. So according to the characteristics number 1, twice C3, 3 sigma V. According to the characteristics number 1, the numbers of irreducible representation is equal to numbers of the classes. Here, how many classes? 3 classes. So T1, T2, and T3. Rule number second, the sum of the square of the dimension is equal to order of a group. Suppose dimension of this representation L1, L2, and L3. In case of C3V point group or ammonia molecule, symmetry elements, numbers of the symmetry elements is equal to 6. Means order of a group is equal to 6. So L1 square plus L2 square plus L3 square is equal to order of a group. This is the characteristics number second. The sum of the square of the dimension is equal to order of a group. Okay. In case of ammonia molecule, order of a group is equal to 6. And this is possible if any two dimensions, any two representations are one dimensional and another one is two dimensional, then and then this equation can be satisfied. So if we take 1, 1, and 2. Suppose this one is character 1 C3. This is character 1 sigma V. According to the rule number 3, the sum of the square of the character is equal to order of a group. The sum of the square of the character is equal to order of a group. So 1 into 1 square, 1, plus 2 into character 1 C3 square, 3 into character 1 sigma V square is equal to order of a group. Order of a group is equal to 6. The character may be plus or minus, but to maintain the criteria of, to maintain the uniformity of any character table, first irreducible representation should be with respect to plus 1. So if we take plus 1, so this can be satisfied. 1 and 1. To get the character for the second irreducible representations, character 2C3, character 2 sigma V. According to the characteristics number 4, any two irreducible representations are orthogonal to each other. Means 1 into 1 into 1 is equal to 1, plus 2 into 1 into character 2C3, plus 3 into 1 into character 2 sigma V is equal to 0. Now this equation can be satisfied if the value for character 2C3 is equal to plus 1 and character 2 sigma V minus 1, and then this equation can be satisfied. But this can satisfy the characteristics number one. Second, third. The sum of the square of the character is equal to order of a group. 1 into 1 square, 2 into 1 square, 3 into 1 square minus 1 square is equal to 6. Means second representation should be 1, 1 and minus 1. Now to get the character for third irreducible representations, any two irreducible representations are orthogonal to each other. So possible T1 and T3, 1 into 1 into 2, 2, 2 into 1 into character 3C2 plus C3, 3 into character 3 sigma V is equal to 0. T2 and T3, 2, 2 character 3C3, 3 minus 1 means 3 character 3 sigma V is equal to 0. Two plus 2, 4 plus 4 character 3C3 is equal to 0. It means value for character 3C3 is equal to 0. Sorry, is equal to minus 4. So character 3C3 is equal to minus 1. Now substitute any value in this equation. 2 plus 2 minus 1 plus 3 character 3 sigma V is equal to 0. So character 3 sigma V is equal to 0. Now Mulliken symbols. This is one dimensional. A or B later can be used. But the value for plus 1 means A. This is also A. This is two dimensional. E can be used. Now there is no perpendicular C2 axis in case of C3V point group. So this is the character plus 1 means subscript 1, minus 1 means 2, 0 means no value. So dear students, this is the construct the character table for ammonia molecules, or we can say construct the character table for C2V point group. Explain the different areas of the character table. So dear students, one thing remember that construct or derive the character table and explain the character table, both are the different thing. Explain the character table, it means we have to explain or describe each area of the character table. So character table can be represented as, we suppose C2V E C2 sigma xz sigma V yz A1 A2 B1 B2 1 1 1 1 1 1 minus 1 minus 1 1 minus 1 1 minus 1 1 minus 1 minus 1 1. Okay, and then we have to mention that Z RZ X RY Y RX X square Y square Z square XY XZ YZ. In case of C3 character, but E to YC3 3 sigma V A1 A2 E 1 1 1 1 1 minus 1 2 minus 1 0. Z RZ XY Rx Ry, x square plus y square z square, x square minus y square xy xz and yz. Dear students, this is the area number 1, area number 2, area number 3, and area number 4. Area number 1, area number 2, area number 3, and this is area number 4. Okay, so first of all, we have to give the definitions of the character table. We already discussed that the devices can be utilized to for the molecular symmetry, and group theory is known as character table. Now we have to explain the different areas of the character table. This is the area number 1. These are the characters. Area number 1 represents character. And how to find out the characters? We have to operate different symmetry operation on the molecule and find out the changes, and that changes can be represented as a character. Area number 2. Area number 2 represents Mulliken symbols. And how to get the Mulliken symbols? We already discussed that if the representation is one dimensional, then capital letter A or capital letter B can be used. If the character for main principal axis is +1, capital letter A can be used. If the value for character is -1, then capital letter B can be used. If the representation is two-dimensional, then E can be used. If the dimension is three-dimensional, then T or F can be used. Now, subscript 1 and 2, we already discussed that if perpendicular C2 axis to the main principal axis and the character of that irreducible representation is +1, then subscript 1 can be used. If the character for perpendicular C2 axis is -1, then subscript 2 can be used. Now the value for sigma h. Character for sigma h is equal to +1. Then single prime, it means A1 dash, A2 dash, single prime can be used. And if the character for sigma h is -1, then double prime can be used, just like a A1 double dash, A2 double dash, etc. And lastly, the value for character I is equal to +1, then G can be used, otherwise subscript U can be used. Okay, if the character for small I is equal to +1, subscript small g can be used, and if the character is -1, G subscript can be used. So I think this is the area number 1 and area number 2, the explanation of area number 1 and area number 2. Now area number 3, this is nothing but the Z, X, Y, Rx, Ry, Rz. Here area number 3, Rz, X and Y. Means area number 3 represents p orbitals, means rotation along the x-axis, y-axis and p-axis. So area number 3 represents p orbitals, just like a p orbitals, or we can say rotational axis. This is nothing but the rotational axis, which can also represents s orbital, p orbital. Okay, so anyhow, this is the rotational axis. Area number 4, so x square, it should be x square plus y square, x square plus y square, z square, x square minus y square, xy, xz, yz. Means these all are the transformation properties, or we can say this respect to d orbitals. Okay, dx square plus y square, dz square, dxy, dxz, dyz. Okay, So these are the transformation properties. So area number 1 represents characters, area number 2 represents molecular symbols, area number 3 represents rotation around p orbitals, and the area number 4 represents rotation around along the d orbitals. Okay, so this is the explain the different areas of the character table. So now we are going for the another title. Applications of the group theory. Only two applications are in our syllabus. First one is atomic orbitals, and second one is sigma bonding. So let us start with the first applications. Applications of group theory to atomic orbital. We know that x is equal to r sine theta cos phi, and y is equal to r sine theta sine phi, and z is equal to r cos theta. So we can represent as a px r sine theta cos phi, py is equal to r sine theta sine phi, and pz is equal to r cos theta. Now, applications of group theory to the atomic orbital. So with the help of group theory, we can predict that how many s orbital, p orbitals involved in the bonding orbitals. So with the help of this group theory, we can predict that contributions are either s orbital, p orbital, or d orbital in the bonding skeletal of the molecule. So let us start first with the water molecule. Let us consider water molecule. It consists E C2 sigma Vxz sigma V YZ symmetry operation. Symmetry elements. Now let us start first with the s orbital contribution. Okay, with the help of this character table, we can predict how many hybrid orbitals involved in the bonding skeletal of the molecule. So let us start with the first oxygen atom of the water molecule. So let us start with the s orbital, and we know that the shape of the s orbital is spherical. Now, if we operate identity symmetry operation, there is no change in the position of the on the shape of the s orbital, or we can say spherical shape of the s orbital. So character is +1. If we operate C2 symmetry operation, so C2 operation means there is no change in the spherical shape of the s orbital, so character is plus 1. Similarly, if we operate sigma vxz and sigma vyz symmetry operation, so there is no change in the spherical shape of the s orbital. So this one is corresponds to even irreducible representation, and it can be indicated by z orbital. That is already mentioned in the character table, and character table will be provided in your exams. So remember that this corresponds to even irreducible representations, or we can say this is the contribution from the s orbital. So next one is p orbital. E into px. So E into Px is equal to E into R sine theta cos phi is equal to Px. So character is equal to plus 1. So there is no change. It means character is equal to plus 1. Next one is C2 into Px. C2 R sine theta cos phi. Now, here theta remains unchanged. Phi changes to phi plus pi is equal to R sine theta cos pi plus pi is equal to R sine theta. Cos A plus B is equal to cos A cos B. Cos pi minus sin pi sin pi is equal to R sin theta. Value for cos pi is equal to minus 1 minus cos pi, and sin pi is equal to 0 is equal to minus R sin theta cos pi is equal to minus Px. So Px becomes minus Px. Px becomes minus Px. It means character is equal to minus 1. Similarly, sigma Vxz into Px, sigma Vxz, R sin theta cos phi. So there is no change. It means R sin theta cos phi is equal to Px. So the character is equal to plus 1. Similarly, C2V E C2 sigma Vxz sigma Vyz. 1 minus 1 and 1. Now sigma Vyz on Px is equal to sigma Vyz R sin theta cos pi. Pi changes to pi plus pi because reflection always at 180. R sin theta cos pi plus pi is equal to R sin theta cos pi minus sin pi is equal to minus R sin theta cos phi. Cos pi is equal to minus 1, sin pi is equal to 0 is equal to minus Px. So character is equal to minus 1. So to give this character, now this corresponds to 1 minus 1 1 minus 1 1 minus 1 1 minus 1, and this is respect to px. We already discussed that this is the rotation along the x-axis. So this is the contribution from px, and this is b1 irreducible representation. So dear students, we can predict that this is the contribution from px, or we can say this is the transformation properties from px. Similarly, we can for the py and pz. So this is y means b2, 1 minus 1 1 1. pz, this is pz, a1. Okay, so dear students, this is most important question for you. Give the transformation properties of the oxygen atom in the water molecule. So this is the contribution from px, this is the contribution from py, and this is the contribution from pz. Okay, we already discussed about the z axis, that is the contribution from a1, irreducible representation. So this is the most important questions. Give the transformation properties of oxygen atom in the water molecule. So first of all, we have to explain the contribution from s orbital. Then we have to operate different symmetry operation on the px, and similarly we have to go for the py and pz. Just we have to mention the py and pz, and we have to derive the px. Okay, so these are the different transformation properties of the px, py and pz. Now we can predict the transformation properties from the d orbital also. C2v e C2 sigma vx sigma v yz, a1 a2 b1 b2, 1 1 1 1 1 1 1 1, minus 1 minus 1 1 minus 1 1 minus 1 1 minus 1 minus 1 1. Okay, so in the case of the water molecule, z, that is we already discussed, rz, xy, ry, rx, x square minus y square, z square, xy, xz, and yz. We already mentioned that the contribution from s orbital, p orbital, s orbital, and p orbital. These are the p orbitals. Similarly, we can predict from the fourth area number 4. This is nothing but the dx square minus y square and dz square. So dxy, dxz, dyz, dx square minus y square. This is the contribution from a2, b1, b2, and a1. So dear students, these are the contribution from s orbital, p orbital, and d orbital. Just we have to write from this character table, that is the contribution of d orbital. We have to prove only for the px and s orbital, and just from the character table we have to write only py, pz, and d orbitals. So these are the transformation properties of the oxygen atom in the water molecule, and this is the most important question for your external exams. Now, if you go for the combined p orbital for px, py, and pz, then what will happen? Okay, finally, we can predict that px, py, and pz from the character table. One minus one minus one, 1 minus 1, 1 minus 1, 1 minus 1 minus 1, 1. A1, A2, D1, D2. This is the contribution from PZ. This is the contribution from PX. This is the contribution from PY. So this is one dimensional, one dimensional, one dimensional. So we can represent it reducible representation A1 plus B1 plus B2. This is one dimensional, this is one dimensional, one dimensional, one dimensional. Okay, so we can prove that all dimensions are the one dimensional. Now, if we operate a combined symmetry operation on Px, Py, and Pz, if we operate identity symmetry operation, so there is no change in the position of Px, Py, and Pz. So we can write the matrix for identities 1, 0, 0, 0, 1, 0, 0, 0, 1. If we operate C2 symmetry operation on Px, Py, and Pz, so character of this matrix is equal to 3. Character means summation of diagonal elements. If we operate C2, then what will happen? We have to consider water molecule along the z-axis. And you operate C2. It means y and z becomes minus Px, minus Py, and Pz remains as it is. So we can write the matrix for the C2 minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1. The character of this matrix is equal to minus 1. If you operate Px, Py, and Pz, if you operate sigma v exit symmetry operation, so x and z remains as it is, Px minus Py and Pz. The character, so matrix for the sigma v xz is equal to 1, 0, 0, 0 minus 1, 0, 0, 0, 1. So character is equal to plus 1. Similarly, for sigma yz, minus 1, 0, 0, 0 minus 1, 0, 0, 0, 1. Character is equal to 1. So after all, C2v E twice C2, C2 sigma Vxz, sigma Vyz. Three-dimensional, minus 1, 1, and 1. Now, with the help of relation between reducible and irreducible representations, that is Ni is equal to 1 upon H, summation of character R into R, N into character I into R. So with the help of this equation, we can conclude that T is equal to N1 is equal to 1 times, N2 is equal to 0, N3 is equal to 1, N4 is equal to 1. It means TR is equal to A1 plus B1 plus B2. So this is the three-dimensional, and we can reduce into one-dimensional, three one-dimensional irreducible representations. So dear students, this is the applications of group theory in the atomic orbital. And in this title, the transformation properties is the most important questions. Now we are going for the last applications of our group theory, and the last title of our unit is the applications of group theory in the sigma bonding. So dear students, we are going for the last title of our topic is the applications of the group theory in the sigma bonding. So first of all, find out the different symmetry elements are present in a molecule. Find out the point groups of these molecules and find out the point groups of a molecule, and then consider the sigma bonding in form of the vectors and operate different symmetry operation on the vectors and find out these changes, and that changes can be represented in form of the matrix, and with the help of the reducible and irreducible representation we can find out the how many hybrid orbitals are involved in the sigma bonding. So let us start first with the ammonia molecule. C3V E twice C3 3 sigma A1 A2 E 1 1 1 1 1 minus 1 2 minus 1 0 and the character table for C3V point group. This is J RZ XY RX RY x square plus y square z square x square minus y square xy xz and yz. So first of all, we can consider three hybrid orbitals in form of the vectors as a nitrogen. We know that the ammonia is a pyramidal. We can consider three vectors v1, v2, and v3. If we operate identity symmetry operation on the three vectors, so there is no change in the position of the vectors, just like a v1, v2, and v3. So matrix representations for the identity can be represented as 1 0 0, 0 1 0, and 0 0 1. So character of this matrix is equal to 3. Next one, v1, v2, and v3. If you operate C3 symmetry operation, so v2, v3, v1. So matrix representations for 0 1 0, 0 0 1, 1 0 0. It means character is equal to 0. If we operate sigma v, so what will happen? 1 0 0, 0 0 1, 1 0 0, 0 1 0. One remains unchanged, another two are interchanged. So character is 1. So after all, so how to find out the how many hybrid orbitals involved in the sigma bonding? So first of all, find out the symmetry elements are present in the molecule E, C3 plus, C3 minus, sigma Va, sigma Vb, and sigma Vc. Point group of this ammonia molecule is C3V point group. So this is the character table for C3V point group, and you will be provided this character table in your exam. So first of all, perform the symmetry operation identity on the three vectors. Consider all the sigma bonding in form of the vectors, and then find out the changes. Now, C3V E twice C3 3 sigma V. This is three dimensional. The character is 3. Identity character 3, 0, and 1. With the help of character table and Ni is equal to 1 upon H, character R into R into N, character I into R. So the value for A1 is equal to, N1 is equal to 1, N2 is equal to 0, and 3 is equal to 1. How to derive it? So 3, 1, 1. N1 is equal to 1 by 6. 3, 1, 1, 3. 0. 1, 3, 1. It means 3 is equal to 1. N2 is equal to 1 by 6. N2 which corresponds to A2. 3, 1, 3, 0, minus 1, 1, sorry, 1, 3, minus 1. It means minus 3 is equal to 0. And 3 is equal to 1 by 6 and 2, 3, 1, 6 plus 0 is equal to 1. So the value for n1 is equal to 1, n2 is equal to 0, n3 is equal to 1. It means tau sigma or reducible representation is equal to A1 plus E. A1 plus E. Why? N1 is equal to 1, E2 is equal to 0 means there is no involvement, and E plus E. Now A1, that is from S orbital, or we can say dx square minus y square and z square. This is from xy, or we can say dx square minus y square, xy, xz and yz. So from this we can predict that either sp3 or sd3 hybridization in case of the ammonia molecule, but d orbital is the distance of d orbital is very large, so we can predict only contribution from the p orbital. So this is the sigma bonding in ammonia molecules. So dear students, with the help of this character table and with the help of the group theory, we can predict the contribution of the s orbital, p orbital and d orbital in the hybridization of any molecules. So I think this is the end of our this topic. So I tried a lot to make it easier. So dear students, I am very thankful to you for the listening me very silently. I am very thankful to the management of the KBS college as well as principal Dr. Poonam Chauhan madam to give me opportunity, as well as head of the department Dr. Khushbu Desai madam to provide me this platform to share my views of the symmetry to the students. And I'm also thankful to the all the students to listening me very silently. So thank you very much. Thank you very much once again, Khushbu madam and Abhishek sir also. Thank you, madam. Madam, your microphone is mute. તમારો માઇક્રોફોન મ્યુટ છે મેડમ.